This is on page, I believe, 18, and it just says further examples. And part of this is going to be about what I said earlier, which is that yesterday I told you if an electron in an atom goes to a higher level, it's because it absorbed a photon. And I just told you at the beginning of today, there are other ways to get it up there. So keep that in mind. What we are asked here is a very general statement. We've got some energy levels within a mercury atom. They're not all shown to you, just the ones we're going to need. And we want to explain or describe what happens in each situation. So you have one energy level diagram to look at. For each of these, A, B, C, D, E, is there an F? F, I'm going to have two energy level diagrams that I'm going to be drawing stuff on. If you feel the need to copy this down, then you need to have another piece of paper where you're drawing these energy level diagrams. But my feeling is most students don't. At the bottom of my screen here, I have an electron and I have some photons. Okay. Maybe this first photon beside the electron is a violet photon. Maybe this photon in the middle that's really big, and I don't know why it has that border around it, is an ultraviolet photon, and this is a red photon. Okay, and I'm going to be using an arrow to indicate motion. So A says an electron with 7.2 eV of kinetic energy collides with an atom in the ground state. So you need to understand that there are two electrons we're talking about. If I say the atom is in the ground state, then that means there is an electron in the atom in the ground state. But I'm telling you that atom is going to be hit with another electron, a bombarding electron, and that bombarding electron is going to hit the atom, and it's carrying with it 7.2 eV. Now, I'm about to explain why the collision occurs between the electron, and it's an oversimplification. But if we assume the electron is in some kind of orbit around the nucleus, and I hope you would agree that the electron's moving very fast around the nucleus, it's a blur of itself around the nucleus. And in fact, if I were to touch the atom, I'm going to touch the electron first. So again, an oversimplification. What this means is that when this bombarding electron hits the atom, it actually hits this electron that's in the ground state. If the bombarding electron is allowed to, or able to, or can give energy to the atomic electron, then the atomic electron would go to a higher level. Right? And the bombarding electron would lose some of its energy. What we always assume, well, I'm going to say always, and if we run into an exception, we'll talk about it. What we always assume is that the atomic electron will always go to the highest energy level it's allowed to. So that's the puzzle I'm leaving in your hands here for a minute. I want you to figure out where the atomic electron can move to. Can it move to E2? Can it move from E1 to E3? Is it allowed to go... Now, be careful here. When I say, is it allowed to go from E1 to E6? Yes, it's allowed to. What I'm asking is, can it under these circumstances? And I'm glad to see most of you have a calculator in your hand, and I'm guessing you're doing some subtracting here, or maybe you're doing some adding. And just put your hand up and down if you are pretty confident you know where that atomic electron is going to land afterwards. So I would ask you, if you're wondering what's going on here, how much energy is needed for the atomic electron to go from the ground state to the n equals 2 state? And just looking at these, without even subtracting, do you see that's about 6 eV? A little bit less. I think it's 5.9, isn't it? does the bombarding electron have enough oomph to pop that electron up? Sure. How much energy is required to go from the ground state to the n equals 3 state? Well, I think that's more than 8, isn't it? Isn't that 8.1 eV? There's a way to do, how many of you worked this out and said it's going to be E2 and you did it by subtracting? There's a way to do it without subtracting. It's to simply say, if I take the initial energy of the electron in the atom and I add the energy that the electron that's going to hit the atom has, if the atomic electron could take in all of that energy, the atomic electron would end up with negative 8.8 eV of energy, which is someplace in here, which is not allowed. And that tells me it's enough energy to pop it to the second energy level, but not enough to get it to the third. It's either at the second or the third. It can't be in between. So what happens, and you're going to write this down. I'm just verbally telling you what happens. What happens is afterwards, the electron in the atom will be in the excited state that's n equals 2, and the bombarding electron will ping off of the atom somehow, but it will have less energy than it did. A lot less. How much less? In other words, here's an exam question. After the collision, what's the kinetic energy of the electron that hit the atom? Well, it's going to be the 7.2 minus whatever that costs to move the electron in the atom up. So you do have to subtract this. And is this, in fact, 5.9? I didn't get a resounding yes earlier. Is that what it is? It is. So it's conservation of energy. If that bombarding electron had 7.2 eV and it had to give up 6.9, 5.9, I believe that's 1.3 eV remaining. So the answer to the question would be the atomic electron ends up in the n equals 2 level, or we could just say the atom ends up in the n equals 2 level. And the bombarding electron continues on its way with only 1.3 eV of energy. Are you with me? So on the one hand, the bombarding electron doesn't have any quantum rules tied to it. It can lose however much energy it wants. But since it's losing energy to something that is restricted by quantum values, there's kind of a restriction on it as well. Let's try another one. An electron moving at a particular speed collides with an atom in the ground state. Well, listen, the only thing that's different here is you have to figure out the energy of the bombarding electron first. You need to do a 1/2 mv squared calculation for this electron. Take the number of joules and convert it to eV, and then it's the same as question A. I mean, the result won't be the same, but it's the same thought process. So 0.5 times 9. 0.5 times 9.11 multiplied by 10 to the negative 31 multiplied by that 1.28 times 10 to the 6 squared. We're just using 1/2 mv squared. It's this many joules? Yes? Okay. Convert to EV. And I mean, we're back at this whole... There's too much in the course and there's too much happening with some of these things where if you had to write everything down, you would never get any answers. You'd never get the work done. So these calculations should be fairly basic. We are talking about 4.66 eV of energy. Well, this is actually very easy to answer. You know, I don't want to say nothing happens. There's got to be some collision between the electron and the atom. But no transfer of energy happens. It's impossible. Because we've already established that from here to here was 5.9 eV. Was 5.9 eV. Well, sorry, this electron doesn't have enough energy even to pop it up one level. Doesn't matter how many of these electrons pound away at that atom. That atom's going to stay in the ground state. And by the way, they can't team up. It's always a one-to-one collision. Does it make sense that the atom will still be in the ground state and the kinetic energy of the bombarding electron will still be the same? All right. A photon of wavelength 460 nanometers collides with an atom in the second energy state. So the electron in the atom starts here, and this time it's a photon. Now let's see. 460 nanometers is visible. It's bluish. So that's this photon. For whatever reason, my colors seem to dance around in these files. So there's my blue photon. Before it was violet colored. Doesn't matter. And I'm glad to see that I suspect many of you have already calculated the energy of that photon by taking 1242 divided by 460. And Sasha, what did you get for the electron volt energy? 2.7. 2.7? Okay. Can I ask exactly 2.7? Okay. And I wasn't sure, but I think I've designed this so that we don't have to worry about a bunch of decimals here. So now the question is, can the electron in the atom, well, it's the only electron there is, can it absorb that photon? How much energy is required to move the electron from 2 to 3? Well, let's see. 2 to 3 would be negative 0.84, nope, negative 8.4 minus negative 10.6. Well, that photon has enough energy to do it. Just hang on to that thought, though. Okay? Just hang on to that thought. Does the photon have enough energy to pop it to the third level? Well, let's see. Negative, or to the fourth. Negative 7.9 minus negative 10.6. Oh, bang on. So it will go, the electron in the atom will end up being in the fourth energy level. And what about the photon afterwards? It's gone. It doesn't exist anymore. Now, we're going to get a question that's very similar to what I'm about to ask. But just look up here for a second, and I'm going to change this question. Don't do any changes. I just want us to think a bit. What if that fourth energy level was exactly 8 eV? What if? Well, negative 10.6, whoops, negative, wrong one. I want this to be exactly 8 eV. Okay. So if we take negative 8.4 and subtract negative 10.6, we get 2.2. I'm going to ask the question I asked earlier. Does this photon have enough energy to cause that to happen? How many of you understand there's something wrong with my question? What's wrong with that question?
To be the exact.
Right. It has to be an exact value for the photon because the photon will either be absorbed or not. So, can you do me a favor and take negative 8 minus negative 10.6? You're going to get 2.6, right? What about negative 3.53 minus negative 10.6? You're going to be past 2.7. The photon wouldn't be absorbed. It's not going to pop the electron off up into a higher level and then take off with less energy. It can't, because it's colliding with an electron in an atom, and the photon will either be absorbed or not. And the only reason why I went into that kind of detour is because as soon as I said, does the photon have enough energy to cause it to happen, I thought I probably shouldn't have phrased it that way. The photon must be absorbed or not. So afterwards, there's no photon. Let's move on. A photon of wavelength 345 collides with an atom in the second energy state. Look at that. My electron now is blue. No idea why. Electrons have no color anyway, so it doesn't matter. And 345, that's ultraviolet. That's less than 400. And we would need to know how much energy that is. Which would be 1242 divided by 345, 3.6 eV. So here's another way for you to decide what's going to happen. On your calculator, take the energy that the electron has right now and add 3.6 to it. And if you get a number that matches an energy level, then the electron will absorb the photon and go up to that particular level. So we don't have to subtract. You could do it this way. You could go negative 10.6 plus 3.6. Because it's a photon, if it's going to be absorbed, it has to be entirely absorbed. Is there an energy level that would have the electron with negative 7 eV? No. So what happens? The photon just continues on its way. I'll let you write that down first. So afterwards, the electron will still be in the second energy state, and the photon will still, well, even this, I was just getting ready to say the photon will still have that much energy. Of course it will, because it wasn't absorbed. This would explain why, for Mercury, in the dark line spectrum for Mercury, photons of wavelength 460 would be missing from the rainbow. Because in a cool gas, the electrons are typically in lower energy levels. So I blast that mercury that's in a cool gas with all of the wavelengths of light from a black body. These wavelengths get swallowed up every time they hit an atom, so they disappear from the spectrum. These do not. And I hope you're starting to get the idea that it's probably very few of the whole spectrum that are lucky enough to get swallowed up. Right? Most photons just won't have that right energy, that perfect amount of energy. E, an electron with a kinetic energy of 9.4 eV collides with an electron, or an atom rather, in the third energy state. Okay, things are going to get a little interesting. You see what happened there? My electron, which was black, became blue when I drag it off. That's weird. Okay, so we have 9.4 eV of energy. And the electron in the atom is in the third energy state. So what's going to happen? This is a tricky one. Alex?
Will it be freed from the atom?
Can you not use the word "it" when you say that?
Will the electron in the third energy state be freed from the atom?
Yes. The atom will be ionized, Because to go from, and this is why using 0 at the top is sometimes helpful, to go from E3 in this mercury atom to E infinity, where the electron's free or ionized, requires an addition of 8.4 eV. And this electron has more than enough energy to do that. So afterwards, the electron is free. And I mean, I want to put it here. Well, let's put it there. But that, make sure you understand, when we write the electron there on your diagram, or you say it's in the ionization state, that means it's so far away that it's considered not part of the atom. It's not bonded to the atom anymore. And, I mean, this other electron is not absorbed. It's still an electron. How much energy do you think each of those two electrons has? Well, the answer is we can't tell. You can't tell me how much energy this electron has and how much the other one has. But you can tell me how much kinetic energy they have collectively. You can tell me what the kinetic energy of electron 1 plus kinetic energy of electron 2 has to be. And it's not 9.4 eV. It's only 1 eV. Because to get the electron to get here requires an addition of 8.4 electron volts of energy. That's spent. If you want to know where it is, it's in potential energy of that electron, because it's further away from the nucleus. That's oversimplified, but think of it that way. So all this means is there's 1 eV of kinetic energy between both electrons. There are probabilistic formulas in physics that you can use not to predict how much energy one electron will have and how much the other one will have, but they will predict that 22% of the electrons will have an energy within this range, and 38% will have energies in this range. It's complicated. And I don't mean to just hand wave it away, but it is. And we can't get into that here. Finally, and this is all about getting you to think of conservation of energy and the fact that photons are either absorbed or not, unless they collide with a free electron, which is the Compton effect, which doesn't happen here. Whereas electrons can transfer, non-atomic electrons can transfer some of their energy. What do we got going on here? A photon of wavelength 300. Oh, that's easy. We calculate the energy of that, and I believe it's 4.14 eV, which is ultraviolet because it's 300. And maybe what I will do is just explain what I just said. We calculated it in electron volts, and I said that's 4.14 eV, and I said, oh, that's ultraviolet. I don't know it's ultraviolet by looking at the 4.14. I know it's ultraviolet by looking at the 300. And the electron is in the 5th energy level. So what will happen? That's a bit of a brain buster, that one. Okay, so let's start with the fact that a photon is hitting an atom where the electron in the atom is not free, which means it's not the Compton effect, which means the photon is either absorbed or it's not. So let's start with that. Will the photon be absorbed? Well, the photon will be absorbed only if the electron is allowed to take all of that energy. The question is the electron allowed to pick up 4.14 eV given where it is? How many of you say no? How I'm going to say yes. It's yes. Because if it gains 4.1 eV, it puts it past the ionization state where it's free. It doesn't have any quantum restrictions out there. See, when you take an electron in an atom and you move it from here to here, that's not allowed. But when you take an electron in an atom and move it from, say, here to anywhere outside of there, it's allowed, because then the electron is free. So what's going to happen is the atomic electron will be ionized. It will end up being, and I say atomic electron, there's only one electron that we're talking about here. So it will be ionized and it will be moving once it's out, it will have kinetic energy if, and I'm hoping that some of you are seeing what we're talking about here. We've already learned about this. It will have kinetic energy left over if the photon had more than enough energy to make that happen. Well, how much energy is needed for the electron to go from E5 to an ionization state? 3.53 eV. But if it absorbs 4.14, and it gives up 3.53 eV, then it must have a little bit left over. 0.61? 0.61. So it will have a kinetic energy of 0.61 eV. What are we talking about here? This is a photoelectric effect. Except that it's not really, because by definition the photoelectric effect is metals and electrons in metals absorbing photons. But this is exactly an explanation of the photoelectric effect. That those electrons in the atoms have to give up a certain amount of energy to escape the atom to become ionized, and then the leftover is a bonus. It's extra kinetic energy, extra energy that's kinetic. Again, I believe the way I've structured this, the whole point of this exercise is to get you more and more used to working with energy level diagrams, conservation of energy, and thinking about the subtler details here, that you can move electrons up by absorbing photons or by smacking them with something. And in fact, that's what I want to talk about right now, which I never really explained. A bright line spectrum, and we can go back here. In fact, I do want to go back. When we heat up atomic hydrogen and we look with a spectroscope, we see all of these photons, all of them. Well, we see the four visible ones. If you had an infrared and ultraviolet detector and you pointed it in the different angles, you would detect them too. Are you with me? That means that electrons in the hot gas are falling from higher levels to lower levels, right? But if I take, and I actually just want to have a tube here that we can look at. If I take, it doesn't even matter if it's hydrogen, because you would never know. If I take this glass tube that's filled with hydrogen, the atoms are cool right now. That doesn't mean, hey, they're cool. It means the electrons in the atoms are at very low energy levels. There's some collisions occurring and the odd electron pops up and down, but it's not enough to produce a lot of light. When I put it into that 10 voltage power supply, the electrical current passing through here is a whole bunch of electrons going from one side of the potential difference to the other with a very high voltage or high energy, and they're banging into atoms on their way through. And every time an electron passing through the tube smacks an atom, that pops the atomic electron up. Now, all of those electrons that are passing through the tube because of electricity cannot always be hitting all of the atoms all of the time. So some of the atoms are being jacked up by that collision with the electrons in the current, and then when they're not, they fall down, producing the light. And that's what's happening. If you are familiar with the aurora borealis, or the aurora australis, northern and southern lights, that is light produced by atoms in the atmosphere being hammered by particles from our sun trapped in the Earth's magnetic field. Say a stream of protons comes off of the sun, or whatever the particles are. They're trapped in the Earth's magnetic field moving in a circle, and we understand that physics, and they keep ping, 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 bouncing off of atoms and molecules in our atmosphere. And those atoms and molecules get jacked up to a higher energy level, and then they get a little reprieve, and they settle down and give us the light. Why is it so intense in the northern and southern hemispheres? Because the magnetic field is the strongest. And you'll have the most collisions occurring there. And I know at many points throughout this course I say, and we will learn about how these things are all connected. It's very close to coming together. That everything, not everything, most of the stuff we've learned is all connected. Cathode rays. Why are cathode rays green? Because when those rays, which are really electrons, bump into the atoms in the tube, they jack the atomic electrons up, and when they fall, they produce green light. That's why if you turn up the voltage, you get blue light, because you're jacking them up to higher levels, and they're falling through a bigger change. All connected. Anyway, I hope this is starting to kind of, like I said, tie it all together. There are a number of problems you can practice dealing with this. I do have a written response question that I want you working on at some point over the next week, and I'm going to say it's due Thursday of next week. It's due a week from today. It has to do with a Millikan experiment. Okay. Because I think that the underlying things in the question might appear on exams as multiple choice and numerical response questions. So this is the bottom line with Bohr. It's probably not 19 to 21. It's probably, oh, it is 19 to 21. Okay. So you can practice that. I'm going to leave this. I'm going to leave this on the right-hand screen for you.